So in our last class, we discussed about basically two things, mostly Eulerian circuits or Eulerian line, and then Hamiltonian circuit. So we have seen few conditions and properties of these two types of graphs and properties. And then in today's class, we are actually going to discuss about another very important topic in graph theory known as tree structures. So that's very important for practical viewpoint. In our practical life, many times we use this kind of concepts, and in computer science this tree structure plays an important role. Okay, so let us first try to describe this things whole thing using some example. So it's basically a sequence. So here the sequence is basically 4 1 13 7 0 2 8 11 and 3. So what I need to find a monotony increasing sequence in it. So it has to be a subsequence. I need to find a monotony increasing subsequence of it of maximum length. Okay, so what does it mean? It means like here, if I start with 4, then I cannot take 1 because the subsequence cannot take 1 as a element, because then that will be monotony decreasing. So it has to take 13, and if it takes 13, then you cannot take anything else, because there is no number which is strictly greater than 13 in this subsection. Okay, so this is a monotony increasing subsequence of this sequence. Now what I want the maximum length, and I want all the subsequence of maximum length that is monotony increasing. For example, if I start with 1, then I can take 13. If I take 13, then I cannot take any further things, right? So I can go in this way. I can take 4, then I can take 7, then I can take 8, and then I can take 11. Okay, so this is also a subsequence of the whole sequence, but that is strictly monotony increasing. So this length is bigger than this length. So this length of this subsequence is 2, and here it is 4. So my question is, find out all the subsequence that is of maximal length. That means it may happen that there could be a subsequence of this which is monotone in nature, but whose length is maybe more than 4. Or if it is not more than 4, then try to find out all subsequence of length 4. Okay, so that's my point. So can you just quickly tell me what could be other monotony increasing subsequence of this? So I can say that this is one of them. So this is one. Anything else? Any other subsequence that you could find?
Sir,
Which is,
0 to 8, 11.
sorry, what?
0 to 8, 11.
0, 2, 8, and 11. Very good. So this is second one. Then anything else?
0 to 3, 8, 11.
0 to 3. You cannot take 3 because its subsequence will be come here, right?
Oh, sorry, sorry. Yes, sir. Yes, sir. Yes, sir.
You cannot take. So anything else?
1, 7, 8, 11.
1, 7, 8, 11. Good.
Sir,
Third one.
sir,
Yes.
why we cannot take 0 to 311?
0, 2, 3, 11, because this position is also important, right? So it will come here. Otherwise, you can short it and then try to take all the increasing sequence. That will not happen. The position is important. So this 3 cannot come before 2. Okay. Any other? Or
1
they are
to
just
11.
sorry?
1 to 8, 11.
1 2, oh, it's already, oh no, 1 2 1 2 8 11. Very good. So this is for anything else? Anything else? Okay, so now you can understand that here we have how many? 1 2 3 4 5 6 7 8 9, 9 or 10, many integers are here. Now think about the situation if I will have thousands of such things and I need to find all possible this kind of increasing subsequence of say maximal length. Now then you can understand very easily that it would be very difficult for you to find. So one possible search could be start with 1, start with this number, and then look at all the things what could be the next. For example, 4 you cannot take 1, then you have to take 13. If it's 13, then you cannot take anything else. But every time you have to exhaust all the numbers whether anything more than 13 is there in that list or not. That means if you are going to use some arbitrary algorithm, then this searching process would be very difficult. Another thing is that, for example, okay, so I will first try to give you an efficient way to solve this problem. Okay, that can be done very easily by using this kind of technique. So if you remember the whole, maybe I can make this, I can make a copy of it. So, so is it visible to all of you? Yes. So the if you see that the sequence is 4 1, so it's the starting point. So it's my starting point, and first step is write down all the elements in the sequence like this. So it's 4 1 13 7 0 2 8 11 3. Okay. Then the second round, start with 4. Okay. Start with 4 and then find all the numbers which are greater than 4 present in the list. For example, here 13 is greater than 4, so 13 is here. Then 7 is greater than 4, so 7 is here. 8 is greater than 4, so 8 is here. 11 is greater than 4, so 11 is here. Now think about 1. So here you have 1, here you have 1. So start with 1 and find all the numbers. You cannot take 4 because 4 is not on the right of 1. So it should be in this direction. So take 1, then all the numbers which are strictly or maybe greater than 1. So 1, then 13, 7, 0 you cannot take. So then 2, 8, 11 and 3. Similarly, for 13, you can see that 13, there is no number on the right of 13 which is greater than 13. So 13 has no such element. Similarly, for 1, you have, for 7, you have something. For 7, you have only two elements, 8 and 11. So 8 and 11, and so on. Okay. After 11, you cannot have, after 3, you cannot have, no elements are there. So you cannot write anything below 3. Okay. Now come to the next step. So after 13, you can see that there is no such element. So you cannot make a bifurcation further. After 7, you have 8 and 11. So you just draw 8 and 11. After 8, you have only 11 and so on. Now when you come to 8, somebody is here. Okay. Now when you come to 8, so after 8, you can see only 11 is there. So you can put 11, and similarly after 8, 11 is there, after 8, 11 and so on. Now this is your one kind of nice looking image or picture. Now can you tell me what would be the highest length subsequence? Anybody from here, can you be able to mark what could be this? Tell me how
Sir,
to then
4,
read
sir.
4
4.
length, and can you tell me what would be this sequence?
Sir, there are 4 sequences, subsequences of length 4.
Exactly. So you will just need to find the highest such length, right? So the subsequence will be here 4, 7, 8, 11. So we have already seen 4, 7, 8, 11. So this is the subsequence. So highest length 1. Then from 1, if you start with 1, then you have 1, 7, then 7, 8, then 8, 11. 1, 7, 8, 11. So this is also we have already exhausted. Then here also 1, 7, 7, 8, and 8, 11. So it's 1, 7, 1, it's 1, 8. So what is this one? This is 1, what was there? Yeah, so this is 1, 2. So this one, 1 to 8, 11, that is also exhausted. And then you cannot start with 1 because no 8 length. Again here, so 0 to 8, 11. So 0 to 8, 11. Now you can see that very easily, clearly, that there exists no such greater than 4 subsequence in this nicely looking images. So it's very easy to now find. And in computer science, this is called a data structure, and we call it decision tree data structure. Okay. Now, uh, you have might have heard about this dictionary, how the dictionary could be searched very easily. For example, so where I just first I initially make my database. So where I get some of the words, I will just pick it in this way. For example, this is my starting point. Say it starts with A, for example. Now I have, say I have A, B, C, and I have A, B, D, and say I have A, B. What I will do, I will start with A. Okay. Then I have A, starting with A, I have two options. Either it goes to A or it goes to B, right? I have two options in the second level. Either it goes to B or it goes to A. Now from A, it goes to B. Now from B, it has again two options. Either it goes to C or it goes to D. Now suppose in the dictionary you want to check where is AAB. Where is AAB? You start with A, then take the decision where you find A. So you will take suddenly this path, you will suddenly take this path, and then from A you find where it goes to B, take this path. Okay. So you can understand, once you have saved in this manner the all the words that you are looking for in this manner, then searching problem is very easy. So you can very easily search very quickly. Just you need to take three steps. Otherwise, what you have to do at the initial level, you have to first make this whole, whether it's with AAB, checking with this. If it fails, then you have to check with this, then you have to check with this, and in each checking you have to check three of the alphabets, right, for each. So A matches with A matches with B or not, then B matches with C or not, then the same thing here also, and then same thing here also. But if you are able to make your database, or if when you save your database in this way, then searching is very easy. Just in three steps you will find your destination. Or if say I have given AAE, then when you come here AA, then when you find that there is no path from A to E, then your conclusion will be no such word, or the name is mismatched. For example, when you just press Control F, so when you search Control F in your computer actually sometimes does like this. So it's very easy. That's why computers are very fast. Google also does the same thing. So there are plenty of such applications of this tree structure in real life. Another thing is that, for example, most of you might have your Facebook account. Suppose you are one of these users, say A is one of the users. So you have plenty of friends. Suppose you have, say, plenty of friends. So you are connected with them. It might happen that this guy is connected with him, this guy is connected with him, this guy is connected with him, and maybe this guy is only, you are the only friend of this guy. Okay, say he is, say, isolated kind of thing, only you are the only friend, and say this guy and this guy, they are all connected. So you can understand that all of them actually they form a huge network, and this network is basically made up of lots of edges and lots of vertices. So how the vertices are defined? Each of the account holder may be considered as a vertex, and you can have a relation like if both of them they are friends, then you have an edge from here to here. Now sometimes you get the request that somebody sends you the friend request. How the WhatsApp, or how not WhatsApp, how the Facebook, they come to know that who could be your mutual friends. In LinkedIn you also find the similar situation. So suppose this guy is a friend of this guy, not a friend of this guy, but then the Facebook will send a request from here because he knows that he is the mutual friend of him. So he sends a request to him automatically saying that would to be a friend of mine or something. Then because this Facebook comes to know through him that he could be a common friend of this. So in that way, graph theory plays an important role. And here sometimes the who is more popular in a class, or sometimes this kind of things can also be measured using this graph theoretic techniques, where this concepts of trees playing an important role. So I'll come to this later on. So now I think you have some idea about tree. So this is not a tree, of course, but trees should look like this. So a tree should look like this kind of things. It might have much bifurcation and all. It might have much bifurcation like this. So this is a kind of tree structure. So from this image, and I say that this is not a tree, but this is a tree. Now, can you tell me intuitively what could be a definition of tree without having any knowledge of trees? Just try to find some of the feature that is present here and that is not present here, and that makes that features, both of them are graphs. Okay, so both of them, they do have a vertex, they do have a edge, they do have and some edge. So the question is which particular property that made up of that is that made up of say age and vertices, that is present here but that is not present here. Quickly, can anybody be able to tell?
So there is no
Some,
closed path.
yes. So in tree you can see that all of them they are open. I do not have any path like this, or I do not have any path like this. That means in this structure what I have, I do not have any closed path, or I do not have any circuit. Whereas here I can see that there is a circuit, but here I see that there is no such circuit. But it's a connected graph, it's also a connected graph. So I can now define intuitively, not intuitively, I can now define formally what do you mean by a tree. And that's the basic idea is the concept of, so the what is tree? A tree is a connected graph without any circuit. So now you know what do you mean by circuit. In my last two classes I have already mentioned about it. So it's basically you cannot repeat your vertex except for the starting and the end point because they coincide. That means it's a closed path. Okay. So some authors allow the null tree. That means the tree without any vertices. So some authors they do use this term null tree. Okay. So there are plenty of such applications of this. So you can see that there are plenty of such trees with one vertex, trees with two vertices and three vertices and so on. So it looks nice. So there are called star graphs and all. So as I mentioned, so decisions trees are very important. So some basic properties of trees, and they are very easy and very intuitive. So it says that there is one and only one path between every pair of vertices in a tree. What it says that in a tree, suppose you take with say this vertex is say 1 and say this vertex is 2. It says that in a tree there exists exactly one path between any two vertices. How will you prove? Suppose there exist two different paths from 1 to 2. Then what will happen? Then that will certainly be a so two different paths say after going somewhere where and it comes here and say something here and here. If you join these two, what you will get? You will get a circuit. So in a connected graph you are having a circuit if you have at least two different paths from two different vertices. Then that will certainly give you a contradiction that a tree cannot have a closed path or a circuit. So that means that from every vertex to other vertex, there is exactly one path, right? Now, can you tell me, suppose I have, say, I have, say, this is 1, 2, 3, 4, okay? And I want to travel from 1 to 4. How many edge shall we travel through? Suppose this is a tree and this is a tree again as tree structure. But interesting point is that suppose I am actually traveling through this 1, 2, 3, and 4, and that is the minimum length path. Not only that, it will contain exactly n minus 1 edges. So if you are going from one vertex to another, traveling through n vertices, then it will certainly cover n minus 1 edges. So that is maybe considered as very slick bound because it's the minimum number of edges that it should travel to travel from one vertex to another vertex. Okay, in that way, trees plays an important role in computer science because in case of electronics, suppose you want to have some connectivity between these paths, these vertices. Suppose they are the points where you want to short, like you want to make a connection to make it a short. Okay, and then what you need to find a path. Okay, and if you have a tree structure, then that tree structure will certainly ensure that that many minimum number of wires are required to connect or to make the whole thing to make the connectivity through, if you are basically traveling through minimum number of edges. So that's why it's in electronics also trees are very important. Okay, so the next result says that in a if in a graph there is one and only one path between every pair of vertices, the graph becomes tree. So it's a kind of just converse part of the whole theorem. In the previous theorem, it says that there is one and only path between every pair of vertices in a tree. So you are given a tree and you need to prove that there exists only one and only one path between every pair of vertices. Now it says that on the other way around, it says that if in any graph G, if there is one and only one path between every pair of vertices, then the graph is a tree. It's just the other way around, and that proof is also simple. As I just now mentioned, that a tree with n vertices has n minus 1 edges. That is also very true, and these proofs are very easy. You just read it. It says that any connected graph with n vertices and n minus 1 edges, it's tree. So it's just a kind of opposite thing. In a connected graph, if you have n vertices and n minus 1 edges, then it becomes a tree. A graph is a tree if and only if it is minimally connected. Just now I have mentioned in case of an electronics engineering, so they require minimum number of connectivity through minimum number of edges, and it says that a graph is a tree if and only if it is minimally connected. The proofs are very easy and it's a well written book, so there would not be any difficulty in understanding these results. So as I mentioned, I am following this Narsingh Deo's book, so it's a very well written, and you can see all the things are justified using lots of images. So it won't be any problem for you to read and understand these things. A graph with n vertices, n minus 1 edges, and no circuit is connected. It says about connectivity. In our previous things, it was connected, but now it says that if n vertices and n minus 1 edges there and no circuit is there, then it has to be a connected graph. So now you get all the different kind of characterization of the same thing, that is tree. So it says that that is a graph with n vertices is called a tree if any one of them is satisfied. Okay, so just now we have mentioned. Okay, so there is another concept called pendant vertices in a tree. So what do you mean by pendant vertex? So from the definition, it's quite clear that what is the last, I mean the end vertices. You must have observed that each of the tree shown in the figure has several pendant vertex. A pendant vertex was defined as a vertex of degree 1. That means this kind of vertices, these vertices are pendant vertices. So this is a pendant vertex. Okay. So this theorem says that in any tree with two or more vertices, there are at least two pendant vertices. That means you cannot draw a graph with one pendant vertex. So it should be at least two pendant vertices must be there. Now this is just the problem that I have started with, this increasing sequence problem. Then you can, I think you can very easily now understand how to solve this kind of problem. Okay. So this is the distance and the centers in a tree. So this distance and centers, these are very important while measuring something. So it distance does not mean that in graph theory you cannot say that okay, this is one vertex and this is one vertex, and say this is one vertex joined through an edge. So the distance between, if you measure by a scale, then the distance between this and this, so here the distance is more than that of this, but geometrically or from graph theoretic viewpoint, this edge and this edge does not have any difference. So both the edges are the, I mean quality wise or the property wise, both of them are of the same type. It does not depend on this distance, but the distance here is this number of edges. For example, if I want to measure, say if I have a graph like this, say 1, 2, and 3, and if I want to say that what is the distance between 3 and 1, then you can find that to move from 3 to 1, how many edges that you are traveling. First check. So here you can understand that if you take this path, then it will travel two edges. So if you go through this, it will travel two edges, this and this. But if you travel through this, then you will travel only one edge. So the distance will be minimum among all such paths, the length of all such paths. And what do you mean by the length of all such paths? That means the number of edges that are present within that path. So here If you take this path, then the length of the path will be 2. Whereas if you take this path, the length of the path will be 1. So the distance between 3 and 1 or 1 and 3 is the minimum of 2 and 1, that is 1. So is it clear? Now quickly tell me what is the distance between, say this is 3 and say this is 2, 4, 5, 6, 7. Can anybody tell me what is the distance between 6 and 3? What is the distance between 6 and 3?
4.
Yes. So exactly 4. Since this is a tree, you understand that there exists exactly one path. There is no other path. Here that was not a tree because we had a closed path. But here, since this is a tree, so you can very easily understand there would be only one path, no other path. So minimality here is basically the exact. You don't have to calculate one more. So it's only one path will be there from any two vertices. That's why in tree it has lot of advantages. Okay. So here some, okay, some relation between these trees and all. And okay, so the distance, now you can understand what do you mean by the distance of a graph. Now there is a term called center. Okay, what do you mean by center? So let me just read from here. So in this figure 2.3.7, the four vertices are there. Okay, intuitively it seems that the vertex B is located more centrally than any other three vertices. Okay, so it looks that B is the central vertex. We shall explore this idea further and see if in a tree there exists a center or how many centers could be there. Okay, okay. Then let us try to explore the whole idea. In this connection, a graph, connected graph, the distance between two of its vertices Vi and Vj is the length of the shortest path. Just now I have mentioned. The definition of distance between any two vertices is valid for any connected graph, not necessarily a tree. So it is true for any connected graph, the distance between two vertices. In a graph that is not a tree, there are generally several paths between a pair of vertices. We have to enumerate all these paths and find the length of the shortest one. There may be several shortest paths. For example, suppose I have a square, say I have a square, say I have a square and say the 1, 2, 3, 4. Can you please tell me what is the distance between 2 and 4? What is the distance between 2 and 4?
2, sir.
It's 2. And so you can see that there exist two paths from 2 and 4. You can take this path and then this path. This distance is 2, or you can take this path and this path. Now you understand that this cannot happen if it is a tree, because in tree you cannot have any kind of circuit or something like that. But one interesting observation is that suppose I just join these two. Now this is a complete graph with four vertices, right? Now if I ask you the same question, what is the distance between 2 and 4? What will be this answer?
1.
1. So in case of a complete graph, if we have a complete graph, then suppose usually Kn denotes the complete graph with n vertices. Okay, let U and V be two distinct vertices, be two distinct vertices of Kn. Then d of uv, can you tell me something? D, how much will be d of uv or vu? It will be how much? Yes, it's always 1. Because in case of a complete graph, every vertex is connected with other vertex through an edge. What does it mean? Suppose it's a pentagon with 5 vertices, then the complete graphs looks like this. So all the vertices are connected with all other vertices. Okay. So you can see, take any two vertices, say u and say this is v, then you can always find an edge between these two vertices. That means the distance is always 1. So in case of a complete graph, the distance between any two vertices is always 1. Okay, there is another kind of graph. We call this bipartite graph. That means, suppose a graph is there, then what I have, so for this graph I have the vertex set v, and bipartite means I just partition the vertex set into two disjoint subsets, v1 and v2, non-empty two disjoint subsets. Okay, in such a way that if you take any edge from the graph, that means the graph will be distributed like this. Take any two edge, take any one edge from this graph. Then what you will find? You will find that one end of this edge will lie in V1 and another end will lie in V2. Okay. Is the idea clear? What does it mean? What I say, that suppose you have a graph. So you must have a vertex set. Now we call this graph to be a bipartite graph. Bipartite graph. If the vertex set is being partitioned into two non-empty subsets V1 and V2, such that take any edge of that graph, then you will find that one edge will be from V1 and another edge should be from V2. For example, if I draw like this, suppose I have here and here, suppose I have like this, and say this, okay, and say this. So you can see that, suppose I have total 1 2 3 4 5. So G is a graph with V and E. So here we have 1 2 3 4 5, and here we have E1 E2 E3 E4 E5, E1 E2 E3 E4 E5, right? So 5 vertices and 5 edges. Now the question is this a bipartite graph? Take any edge. Anybody tell me any edge? Say V3. Okay. So I have taken V3. Now I need to partition my V set 1 2 3 4 5 in such a way. What I am saying, my V1 is 1 2 3 and my V2 is 4 5. Now take any edge, for example E3. I have taken E3. Now the two ends of E3 are as follows, it's 2 and 4. So you can see that 2 is here and 4 is here. So take any path, any edge, then you will find that two endpoints will lie in two different vertices V1 and V2. That's why this is known as bipartite. Bi means two, you are making it in two disjoint parts. But there is another concept known as complete bipartite. Complete bipartite graph. How it looks like? Here it says that any edge, take any edge, right, of the graph. Then it says that one endpoint will be from this set V1 and another endpoint will be from V2. Now in case of complete bipartite graph, what it says that it will be like V1 and V2, this part is fine. Now, if you take any point from V1 and any point from V2, then there must be an edge between these two. Okay. Is this graph a complete bipartite graph? And if so, why? And if not so, why not? So, is the definition clear? Complete bipartite, or shall I repeat once more? Complete bipartite means it has to be bipartite. That means it has to be V1 join V2 should be V, and take any edge from here. One side should be, one endpoint should be from V1 and one endpoint should be from V2. What I'm saying, its extra thing is that complete bipartite. What does it mean? It says that if you take any edge from G, in the previous definition it was if you take any edge from V, one end should be from V1, another end should be from V2. Now what I am saying, take any two vertices, one from V1, another from V2. Say this is V1 and this is V2. Then if it is to be a complete bipartite graph, then there must exist an edge between these two vertices. Okay. So then we'll call it complete bipartite graph. Now my question is this graph a complete bipartite graph? If yes, why? And if not, why not? Anybody?
No, sir, it is not.
Why not?
Sir, because there is no edge between 3 and 5.
Exactly. So there is no edge between 3 and 5. So you cannot have, so if you take 3 from V1 and 5 from V2, you cannot have an edge between these two. That's why this is not a complete bipartite graph. But certainly you can have a complete bipartite graph of, say, if I have 3, here 3 vertices, here also I have 3 vertices, then the complete bipartite graph should look like this. Sorry. If I start with this, then say this vertices, oh, what is happening? Like this. So this is a complete, so not yet. This is a complete bipartite graph with 3 vertices here, 3 vertices here. So we call it K33. Now quickly tell me how many edges are there. So it has edge set and vertex set. So what would be the order of A and what would be the order of V? Quickly.
So 27 is
How many?
so 20.
20.
20 no, sir, 27.
20
So,
Sir,
seconds.
3 factorial.
three, no, not three. It's, not 27. 3, 3, 6, 9.
So number of edges is 9 and number of vertices will be
6.
6. So if I write it KMN equal to, say, vertex set and edge set, then what would be the vertex set size and what would be the edge set size?
So Mn and M plus N.
Mn and M plus N. Now tell me why this is 9. Then will it be 9? So how many edges? Let us try to count first. So here 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. But what is this? So here K33, it should be then how much?
Amen, sir.
It should be. So I think you have just made it other way around. Here it was like this. Okay. So I think it should be m plus n, and here it is mn. Okay. I think what you told was correct,
It's the
but I
ages.
think
Yes, the
yes,
ages I told MN. Yes.
yes, yes. Yeah, yeah. It's perfectly correct. Now it's clear to all of you. So the number of, now tell me what would be the distance between two vertices. So here I have say u1, u2, u3, v1, v2, v3. Now if I take, so here we have v1 consists of u1, u2, u3, and v2 consists of v1, v2, v3. Now tell me, so you here it might have two different types. Distance between from say u1 and u2. What would be the distance? And what would be the distance between v1 and v2? And what would be the distance between mixed v1 and say u1? Okay, tell me. What is the distance between u1, u2?
Sir, 2 to 1.
Yes. So if they are from the same vertex group, so they are from the same vertex group, that is from the same vertex group, then the distance is bigger, it's 2. But since it's a complete bipartite graph, it will, if they are from different vertex group, then as I mentioned in the definition, there must be an edge between these two vertices. That's why the distance is 1. Good. Okay. So this concept is clear now. Okay. So let us again come to this d of UV, distance between two vertices, if its vertices UV is the length of the shortest path. Okay. Now, for instance, this path between this, so they are all now very clear. Okay, distance between V1 and V2 is how much? And as you understand, it's when I am going to define this concept of distance, certainly the concept of metric will also come into play. So here the definition of metric, in our normal definition of metric, you will find that if you define the distance between these two, then that will certainly satisfy all the properties of the metric that usually we deal in function analysis or many other places. So here also the metric concept is also satisfied if we define the functions or this metric in that way. Okay. So it says that the distance between vertices of a connected graph is a metric, and that is not very difficult. So there some also very important terms are there, that is eccentricity. That's very important in terms of social relation between how to measure the relation between some person with some other person in a social media by using this term eccentricity. So let us try to define this. Coming back to our original topic of relative location of different vertices in a tree, let us define another term called eccentricity, also referred to as associated number or separation of a vertex in a graph. The eccentricity EV, so eccentricity of a particular vertex, okay, that is V in a graph, is the distance from V to the vertex farthest from V in G. That means, suppose you want to calculate the eccentricity of a vertex V, then what you are trying to see is that calculate the distance between all the remaining vertex from V and take the maximum distance length. So that would be the maximum or the eccentricity of the vertex. Vertex with minimum eccentricity of a graph is called the center of G. Now it will be clear to you. So what is the center and what is the eccentricity then? So eccentricity of a particular vertex is basically try to find the distance between all the remaining vertex and take the maximum one. So that would be the eccentricity of a particular vertex V. Now, so you have to calculate the eccentricity of all the vertices. Now, take the minimum eccentricity, having choose that vertex which has minimum eccentricity, and that will be considered as your center of the vertex. Okay, so let us have a look at this. So tell me which will be the center of this vertex. I'll just cut it from here. So that would be a good exercise, that which will be the center of this graph. Okay, so everything is leveled here properly, so you can easily see all those leveling quite clearly. Now tell me which one would be the center of this vertex of this graph. So you need to calculate the eccentricity of all the graphs. So let's start with, say, V1. So I want to calculate the eccentricity of, say, V1. What I need to check, I need to do the vertex other vertices. So here only V1 and V2 is there. So I just put other naming as well. So this is V3, V4, V5, V6. Any other vertex left? One, two, three, four. Yes. So all of them are done. So when we are trying to calculate V1, eccentricity of V1, what we need to check? We need to check the distance between V1 and all the remaining vertices. So distance between V1 and V3 is 1. Distance between V1 and V6 is also 1. The distance between V1 and V2 is basically how much you have one such path, another path, that is 2. You may also come through this 1, 2, 3. So 2 is minimum. You can also go like this. You can travel like this and then come to V3. So V2, then it would be even more. So the distance between V1 and V3 is basically 2. So distance between V1 and V5, how much? It's again is 2. So the distance between V1 and V4, V1 and V4 is how much? 1, 2, 3. So you have exhausted V2, V3, V4, V5 and V6. So you have exhausted all of them. So what is then the eccentricity of V1? Can anybody tell me what would be the eccentricity for V1?
3, sir.
Is 3, because this is the maximum of all this 1, 2, 2, 1, 1, 2, 2, 3. So here the eccentricity is 3, right? Okay. Now, so to find the center of this graph, can anybody be quickly tell me what could be the center of this graph? So you need to check all the eccentricity of all the remaining vertices. Okay. So I'll just give you somebody. Pratik, can you find the eccentricity of V2? Anubhav, could you find the eccentricity of V5? So this is Pratik, Anubhav, and then maybe who are there? Kolpok for V6, Kolpok, and who are there? Akash, maybe for V4, and Tathagato, maybe for V3, Tathagato. All the vertices are exhausted? Yeah. And the remaining you can do whatever you like, you can do. For remaining you can do whatever you like. Quickly, I will ask everybody, very quickly do it.
Sir, eccentricity of V4 is also 3.
So
V4
V2
is
is 2.
eccentricity of V2 is 2. Okay. Anubhav, eccentricity of what else? 1, 2, 3.
Sir, V6 is 2.
Okay.
Sir, V3 is 2.
2. Okay. And then
Sir, V5 is, I think, 3.
V5 is 3. Okay. Anybody else who checked V5? Quickly
Sir,
try
2,
to.
sir. V5 is 2.
V5 is 2. Okay. Anubhav, have you checked? 1. So just try to check. The distance between this vertex is 1, this vertex is 2, this vertex is also 2, this vertex is 1, and this vertex is 1. So yes, it's 2. It's not 3. Now tell me who are the centers? So you can see that these vertices. So 2 is the minimum. That means V2. So this could be a center, and then V5. This could also be a center. V3. V3 is here. This could also be a center, and V6, that could also be a center. So 1, 2, 3, 4. Okay, very quickly, can you draw a graph, simple graph? It has to be connected, of course, with 3 centers. Can you draw a very quickly graph with 3 centers? So here we had 4 centers. Now I want to find some graph with exactly
So triangle.
3 centers. Okay, triangle. Okay, so who are the centers? So all the eccentricity of all of them,
Is 1.
that will be 1. Any complete graph? So with say K5. So you can understand, so it was K3, and if you take K5, so then if I want some odd number of centers, then I can always make odd number of centers here, right? By considering any complete graph. Very good. Okay. Now there is very interesting result is there regarding center. It's already done. Yes. What happens for a tree that has either one center or two centers? So in here you have already found 3 centers, or even for K5 you will have 5 centers. But in a tree you will have either 1 or 2 centers. You cannot have more than 2 centers in any tree. Okay. So you cannot have a center more than 2 centers in any tree. Either it would be 1 center or it would be 2 centers. So here you can see that from the image it looks like they could be a center. Here also they could be a center. But you cannot have any tree. That's quite interesting. So now quickly tell me which will be the center. Any guess who could be the center? And how many of them? So C could be a center that you can understand. It's almost middle of this. Here also C. Okay, so there is a nice explanation of this. Uh, okay, I think you can do it. It's easy, but the way that it gives you the idea, it's starting from a small thing and then you need to explore in a bigger form. So I leave this proof to you. So please have a look at this. It's very easy and it's written in a nice way. So you can understand it and you can find that there are lots of application of this. There are another two more terms, that is radius and diameter. It's again very easy. So if a tree has a center, one or two, does it have a radius also? So what is the meaning of a radius? Radius and diameter. So how they are defined? So radius of a graph and diameter of a graph, diameter of a tree, they are also very easy to define. So they are basically like minimum of something. I'm not giving you the definition, just please have a look at this and that will be easy for you. You may look for some internet or something, then you will find what do you mean by a diameter of a graph. So it's not even defined only for graph, but it's the definition is defined for radius and diameter is also defined for any connected graph. Okay, so I'm not going to that, but instead what I'm going directly from here to you can skip this part. Okay, they are not within our syllabus, so you can skip this part. I'm directly going to the spanning tree. So what do you mean by a spanning tree? So suppose I have started with a graph. Say I have started with say this kind of graph. Say for example, maybe K4, a complete graph. Somebody joined now. Who is this guy? Okay. Suppose I start with this kind of graph and I want to find a tree inside this. Okay, how do I find? So can you tell me one tree? Uh, so this is of course it's not a tree, but from here I can always find a tree containing all the vertices. For example, suppose I have 1, 2, 3, 4, and upwards I have E1, E2, E3, E4, E5, and E6. So suppose this is E6. Now if I take this, if I take this, then of course this is a graph. So it's a tree as well. So this is a subgraph of this graph with only this vertex with edges this E1, E2, E3. You may think that okay, I can have another. So this is E4, E3, E2. One may say that okay, I'm going for a better one. So like this maybe E1, E6, and then E3. So it's again a tree. Again, one may think, okay, I may go in a different way, maybe like this. So this is E1, E6, and then E4. One may go like this, or even, so I think I have already exhausted this one. So maybe one may go like this. So you can see that there are plenty of such graphs here. Within this graph, you can have plenty of trees which contains all the edges, right? So that is also important because as you understand that this tree grips the minimally connected things. If you remove any one of the edges, this graph becomes disconnected. So it gives you a kind of the concept of minimal concept. That means it's very sleek, it's very slim. That's why if you are given a very complete graph, that means the maximum number of graphs, the maximum number of edges that one can accommodate inside a connected graph, a simple graph, that is the complete graph. Okay, within that complete graph, even how to make some choices so that you will have a tree, that means a minimally connected path or minimally connected things which will give all the vertices. Okay, so that's very important, and that is known as spanning tree, and minimum spanning tree is of great importance. So sometimes it happens that, suppose some cities are there and there are cost from traveling from here to here and so on. So there are say four cities, and say the cost involved here, say this is 40, this is 30, this is say 20, this is 10, so this is 60, and say this is 100. Okay, so there are six different tags or six different costs are given here. Now the question is, if I want to have the minimum amount of cost containing all the vertices, then I need to have a tree, and that tree is basically known as minimum spanning tree. So let us have a look at some example, and there are very interesting constructions or algorithms are there. Two very popular algorithms are there for finding this minimum spanning tree. Just now I have given a connected and undirected graph. A spanning tree of that graph is a subgraph that is a tree and connects all the vertices together. So that's the spanning tree. Okay. So let us try to find the minimum spanning tree. That means I want the cost to be minimum. Okay. Can you quickly tell me? So let us try to have this image. Maybe from here. Okay. Let's see. Okay. Okay. Suppose this is my graph, and say they are the cost of individual ages. So this is the cost of this age. Cost means, suppose it's a maybe travel cost or something. Now I want a tree that will give me the minimum cost. Quickly, can somebody be tell me what could be your strategy, so that at the end, when you travel through that tree, you will have a minimum cost. Mind that it's not a kind of like you have to it has to be Eulerian circuit or something like that, but I want a tree whose cost is minimum. Cost means, so if I want the cost of this whole graph, means you just add all the weights given on the edges. That would be the cost of the whole tree. Now suppose I have only this part, say this to this and this to this through this path, then my cost will be 13, 8 plus 5. Now I want the minimum cost tree containing all the vertices, and the cost will be minimum. How to find such?
Sir, cost of my tree is 47.
Okay, so cost of your tree is 47. Now whether I can have even lesser cost travel? Anybody else who tried? So Akash gave a cost of 47. So what is your route? Can you please give us such route? You start from where?
Sir, I start from bottom.
From here. Okay.
Yes, sir.
You
And
went
then,
this way. Okay,
yes,
let me put the names. One. Okay, maybe I just put it one, two. Okay, let me put it here. 3, 4, 5, 6, 1, 2. Okay, now tell me. And maybe here. So this is 7. Yeah. Now tell me from 1 2, you started with 1 2
2,
2, the cost is
then
4,
7, then 7,
then 7, the cost is
then
12,
3,
then 3, the cost is 2,
2, then 4, cost
then
is 8,
4, cost is 8,
then 5,
then 5, the cost is 5,
and then 6.
and then 6, 6 is 16. So you have exhausted. What's about? Yeah, you have 1, 2, 3, 4, 5, 6, 7. So its cost is 16, 18, 26, 31, 47. Okay, so your cost is 47. Very good. Now anybody else? Anybody else? Anybody, will you try? Okay, so let's have a look at this. What is this cost? This cost is 42. So here he has taken 4, 12, then 2, 3, 5, and 16. So how can you please 16, 16, 32, 32, and 10, 42? Yes. So you can see that this cost is even less than your cost. Okay. So the question is, how do I do some algorithm so that that cost will give us the minimum cost? Let us have a look at this. So there are, in this class, I will basically give you two different algorithms, and one is known as Prim's algorithm, another one will be Kruskal algorithm. Let us first explain what is Prim's algorithm. So let me first give you the broader idea, and then I will explain it through some example. So a graph is there. A single graph can may have different spanning trees. A minimum spanning tree, or the minimum weight spanning tree for a weighted, connected, and undirected graph is a spanning tree with weight less than or equal to the weight of every other spanning tree. That's why this is called minimum spanning tree. The weight of a spanning tree is the sum of weights given to each edge of the spanning tree. So now I think it's the definition is quite clear to all of you. Okay, so what is that Prim's algorithm? So what you are given? You are given a basically connected graph. So it starts with an empty spanning tree. So basically you start with a set, and that set is basically you want to make that set. At the end of your algorithm, that set will be your required spanning tree. Okay. The idea is to maintain, you have to have two sets of vertices. One set you start with an empty set, and then another set is there. So now from another set you want to insert some of the vertices from that set into the empty set, so that the set will be bigger, and then this set will be shrinker. And at the end of the day, ultimately what you will end up, you will end up with a spanning tree. So let us try to explain. So what it says, that suppose start with any vertex. So here you have taken this vertex. Okay. So initially this vertex set, say V1 was empty, and V2 is the whole remaining vertex set. So all the remaining vertices, all the 7 vertices are within V2, and V1 was empty. Now the first thing you do is from V2 take this vertex. So here our vertex was, so I have taken V1 and V2. Step 1, step initial step, V1 was empty set and V2 was the whole V set containing all the 7 vertices. So step 1, take any of the vertices. For example, I started with say 1. So inside V1 take 1. So now what is V2? V2 is my V minus this 1. Okay. So you don't have, now it's basically from 2 to 7. Now what it says, have a look at all the edges that it goes out. For example, here you have taken this vertex. Now have a look at all the vertices from where you can move. So from vertex 1, have a look at all the vertices from which you can go through some edge. For example, from 1 you can go to this point, one vertex 6, you can go to vertex 7, you can go to vertex 2, and no other vertices you can go, right? So V1 has degree 3, so you can go to any 3 of these vertices. Now choose that edge to form a spanning tree which will have a minimum weight. For example, among this 4, 14 and 26, 4 is minimum. So choose this edge. So now you have already chosen this edge for your initial step. So in step 2, what you have? Now you have within V1, you have now one more extra, 1 and then 2 is already inserted. Then what is V2? V2 is V minus V1. Okay. Now you look at all the edges that you can move through these two vertices. So from here, you can go from 2, you can go to vertex 3, or you can go to vertex 7. And already from 1 you could have gone to vertex 7 or vertex 6. So take the minimum of 18, 26. So what is minimum? Minimum is 12. So take this one as your path. Okay. Now step 3. So in V1 you have now 1, 2 and 7. So what is V2? V2 is your V minus V1. Now from this point, 3 vertices where you can go, take the minimum one. Okay. But at the same time, you should also keep in your mind that, okay, let's see how it goes. Yes. So take the minimum one, and at the same time, you should look into this algorithm's formal definition. What it says? So the first step consists of the vertex already included in the minimum spanning tree. The other set contains the vertex not yet included. That means V1 and V2. At every step, it considers all the edges that connect the two sets and picks the minimum weight edge from this edge. After picking the edge, it moves the other endpoint of the edge to set containing MST. So what it will do? Now from here, it will find all the minimum weight. For example, here where it can go here, it can go here. Also from here, it can go here. From here, it can go here. So among this, how many, what would be the minimum? So 2, 3, 14, and then 26. 2 is the minimum. So take 2 as your path. So let us go to there directly. Yes. So from here, you just take from here. Okay. Oh, what is happening? Okay. So from here, from you suddenly take this. Now, if you have this at your hand, in the next step, what you are going to do? You will take this one because 3 is the minimum among this. Now, from here, you will have this one, and from here, you will have again this one. Is the algorithm clear to all of you? Is the algorithm clear to all of you? Any
Sir,
question?
the root is not clear yet.
Root is not yet clear. Okay. So let us try to do so. This one. Okay. Let us try to once again make a paste of this and then we'll do this. Okay. So let's start with any point, say this point. For example, for the time being, let's start with this point. So this is our 1, this is our 2, 3, 4, 5, 6, 7. Start with this and try to find all the vertices from where you can go through some edge. So there are only two ways that you can go. Either you can go to this point, or you can go to this point, or you can go to this point. That means you have only three options. Choose the minimum weight edge. So among this 4, 14 and 26, the minimum is 4. So you have to consider this too. That means your edge is basically this one. So this is your first route. Okay, so this is your first vertex that you traveled from here to there. Now you have to now check from all these two vertices which are already in V1. So just now we have mentioned V1 initially empty set and V2 was our V. Then in my second choice, first I started with the vertex 1. Then what is my V? V was my V minus V1. Then in the next step, what is V1? V1 was, I have selected 1 and then 2. And then what is V2? V2 is my V minus V1. Then again in step this, I have to check all the edges from where you can go from these two vertices. So where you can go? You can go either from this vertex, you can go to either 3 or 7. So from 2, you can go to either 3 or 7. For cost is either 18 or either 12, right? And from 1 you can already explore this one, so you do not have to consider this 4. So what are the other places where you can go? You can go from here to this cost is 14 and this cost is 26. So among this, what is the minimum cost? So this is the minimum cost. So you need to choose the minimum cost one. That means you need to choose this path. Okay. So now in V1 you have 1, 2 and 7. Now similarly for V2 is same thing, V
Sir,
minus V1. Yes.
sir, why are we consider one?
Okay,
Matlab,
let's try with any other vertex. Okay. So let's try with
sir,
any other.
when we are on vertex 2,
Yes.
so then we need to come back at 1. Then we can consider 14 and 26.
No, the algorithm says that you also have to, because at the end when you will come to this step, then you will able to see that when you are here, then once you have taken this way and then again you have to take this way. So unless you consider all the vertices, you won't be able to do so. Okay. It may happen, see, all the time it actually maintaining a tree structure. All the time it's actually maintaining a tree structure. Okay, let's start with any other vertex. For example, suppose I have taken this as 1. Okay, say 1, 2, 3, 4, 5, 6 and then 7. Now tell me, from 1 where should I first go? What should be my first move? From 1 where should I go first?
7.
7 by 3, right? So because from 1 I could have gone to 5, 10, 3, and 16, out of which 3 is my minimum. So I have taken 7. Now from here, where should I go? So extra things that we need to consider here is it's 2, 12, 14, 30, and then all the remaining things. So what should be my next option?
Sir, 5 by 2.
By 2, yes. Okay. Then see, in your case, what Akash was telling, why should I go back to 1? Now you understand why should I go back to 1. Because from here, the options are basically 18, 8. From here, the options are basically 12, 14, and 30. And here, the options are 10 and 5, out of which 5 is the minimum. So I need to consider this one. So unless you consider all the things, you won't be able to complete this, but that's the algorithm. So it's given by Prims, so you cannot help. You might have some different algorithm, but according to Prims algorithm is required. And now you can see that one is again important. You cannot just exclude one, right? Now I need to consider 5 because 5 was my minimum among all the things. Now you cannot consider, even if say 8 is the minimum, you cannot consider it, because if you consider this, then that will not be anymore a tree. So you cannot consider 8 again. So what you then, where to go? Which path you should take from 7, 7 or 1? Which one you should take? Which one?
Sir, 7 to 4 by 12.
By 12. Yes, very good. And then you can see that this could be the minimum. And then from here, what left? So you cannot go this is already gone. You cannot go this is already gone. And then the last one,
1 to 2.
1 to 2, and that is 16. Now if you calculate this whole cost is 5 plus 16 plus 3 plus 2 plus 12 plus 4. Please check how much is that. So 16, 16, 32, 32, and 42, the same thing. I think it's the same thing we got by using by the same thing. Yes, so the same thing we get, the same, exactly. So it doesn't matter from where you start. You may not get the same spanning tree, but at the end you will certainly get a spanning tree, but that requires a proof. So the proof is not within our syllabus, but if you are interested to have a look at this, you can have a look at this. So if you search for the proof of Prim's algorithm, you will certainly get the whole algorithm. Okay, why it's actually giving you the minimum spanning tree. Now you can understand it's giving a spanning tree with some weight, but why it's giving the minimum spanning tree? For that it requires a proof, but the proof is out of our scope. But if you are suddenly interested, I'm sure that you are interested, you can just Google it and then you will get the proof of this. So that's Prim's algorithm, and then there is another algorithm that is known as Kruskal's algorithm, the same thing. Okay, what it says: sort all the edges in non-decreasing order of their weights. So you can understand that it has some weights on every edge. Then sort the edges. That means sort means you need to non-decreasing way. So what do you mean by non-decreasing way? It may be a constant or it may be a monotone. So non-decreasing way of their weights. Pick the smallest edge. Smallest edge means take the edge having the smallest weight. Check if it forms a cycle with the spanning tree formed so far. If cycle is not formed, include the edge, else discard it. Repeat this whole process till. So let us try to explore. So you can see that among all these weights, 2 is the minimum weight. So start with 2. Okay. Then you have already taken 2, then take the next minimum, that is 3. And when you are adding this, just check whether after adding this, the new edge will form the form a cycle with the existing spanning tree. So first step was my this. So this is my spanning subgraph. Then you have added this. So this is my spanning subgraph now. Now just before adding 3, you need to check whether that forms a cycle or not. Now what is your minimum? 5 is your minimum. So 2, 3, 5, right? So consider 5 here and also check whether 5 is or there or not. I mean, forming a cycle or forming a closed path or not. Now after 5, you can see that 8 is the minimum, right? After 5, 8 is the minimum. But suddenly you cannot take 8 here. Why not? Because if you consider 8 here, that will form a cycle. So you cannot take 8 here. But instead, you can see that, okay, before that, I think 4 is there. Okay, before 8, I think 4 is there. 4 is there. That's why they have taken 4. But after 4, you cannot take 8, because 8, if you take 8, then it will be a cycle. So instead 8, so you have to discard 8. Then you need to check what is the minimum. So you can see that 10 may be minimum, but if you take 10 here, then also this will form a cycle, closed cycle. So 10 cannot also be taken. So then the minimum is 12. Okay. So you start with this 12, then it's already taken. Then the minimum is 14, but you cannot take 14, right? It's already taken. So you cannot take 14. So after 14, you might have 16. Yes, 16. So you can take 16. And then you have 18. You cannot take 18, or you cannot have 26 as well. So I think it's already done. So you don't have to. Is the algorithm clear to all of you? So first you check that in Prim's algorithm, it was actually making the spanning tree. So all the new vertices are being added which are already connected. You did not have any disconnection here. But here you can see that it was a disconnection. So initially it was like this and suddenly it came here. There is no connection between two. But at the end, when the algorithm stops, it will certainly give you a spanning tree and with minimum weight. Is this algorithm clear to all of you? Is this clear?
Yes, sir, it's clear.
Good. So that's all. What we wanted to discuss today is basically Kruskal's and Prim's algorithms. Again, the proof is out of our scope. So if anybody is interested, he or she is welcome to have a look at this. Just Google it, proof of this Kruskal's algorithm. That will give you the idea how it actually giving you the spanning tree and the minimum spanning tree. That's the minimum weight spanning tree. So any question or comments? If you have, you can ask me.